Good afternoon. Oh, lovely, lovely. It works. It works. So we had a bunch of coroutine talks this week. So who went to at least one of them? Oh, wonderful, wonderful. So my name is Gor Nishanov. I'm a developer in Visual C++ team. And one of the things I work on is design and standardization of C++ coroutines. Most efficient, most scalable, most open coroutine of any programming language in existence. And that is not an accident, because we put a design principles when we started working on that we want coroutines to scale to billions of concurrent coroutines. It means that an overhead per individual coroutine is tiny, 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 just a few bytes. We also wanted coroutines to be very efficient, so that an overhead of suspend and resume is equivalent to overhead of a function call and return. And in those cases where a coroutine is inlined, it disappears completely. Moreover, we wanted to put no restrictions of what can be done to the coroutine and from the coroutine. So from the outside, coroutine is a normal function. You can store it in a stud function, take an address, function pointer, pass to put it on the ABI boundary. And from the other side, there is no restriction of what you can do in the coroutine. Moreover, coroutine can be converted to a void star so that you can marshal it through a C API, and then maybe like OS API will call you back later. You reconstitute the coroutine from a void star and resume it. Also, we did not want to tie the coroutine to any particular machinery, because different category of people have different desires for their asynchronous runtime. So coroutines are open-ended. They can hook up to anything you want. And finally, to increase the applicability of coroutines, we did not want to tie them to exceptions. They will work nicely with exceptions where you want to use them, and in environments where you cannot or just impossible to use exceptions, you can use coroutine just fine. So it's an old thing, very old thing, almost 60 years, invented by Melvin Conway. And Knuth gave this convenient definition that coroutine is a generalization of a function. It has everything that a function has, like you can call it, it can return back to you, but in addition, it gets two more operations, suspend and resume. And if the control flow in a normal function looks like this, where the function will only return back when it reaches the end, in a coroutine, actually a function can return back at some suspend point, and then the guy who calls it, or somebody else, can resume it. It'll continue from the previous suspend point, and it'll keep going until it reaches the end. And in C++, let's look at the dry language of the standard. And it says quite nicely. It just says, a function is a coroutine if it has yield, await, or co-return. And here's an example. It's a simple hello world C++ 20 style, where we have a generator hello, which yields characters one at a time. And then your main in the loop spins and pulls them one at a time. And every time the range base 4 in the main pulls a character, it actually resumes the coroutine. It jumps immediately after yield. It goes to the next iteration, outputs another character, and yields back to main. Or another pattern frequently used is asynchronous task, where you actually await there, waiting for some event to happen, like in this case, 1 millisecond passed. And then coroutine is resumed by, say, a thread pool, and it prints woke up and returns 42. And this is like the bigger example to show how amazingly efficient coroutines are. It's a good bolted version of the demo I showed at the CppCon 2016. So you see, all of those beautiful coroutines composed together, sent to the standard algorithm, result a single constant. Lovely, lovely, lovely. Like C#, try that, or Python. Nobody can match that. Maybe Swift soon, but not yet. So this was the intro to coroutines. Now the main part starts. This summer, we had an amazing standardization meeting in Toronto. We got so many goodies. C++ was shipped to some 3-letter acronym or 2-letter acronym. Richard knows better. It's DIS or something. Anyway, so it was almost there. It was shipped. A bunch of TSs were sent to publication. Ranges, coroutines, networking. Modules went for PDTS ballot. Oh, concepts. Concepts were merged into the working paper for C++20. So many, many goodies. But specifically, we're going to talk about two wonderful gifts we got from Toronto, namely Coroutines TS and Networking TS. Coroutine TS because it makes asynchronous code beautiful, and Networking TS because naturally there is a lot of opportunities to write asynchronous code there. So let's see what's inside. Wonderful. So Networking TS brings us a lot of goodies. We have sockets, UDP sockets, TCP sockets, timers, executors, not the scary one, the smaller ones. And finally, the best of all, IO context, which binds them all together. I even have a slide about IO context. So, okay, well, no. And many more nifty things I want to mention. It's just, I only listed a few. So IO context is the thing, it's like a completion queue. And all of the various asynchronous sources available in the network in TS, they all send their completion to a particular IO context. And then on the consumption side, you decide how do you want to execute them. If you want, you can just call IO context run on your main thread. Or if you'd like to be more scalable, you will launch correct number of threads. It's a difficult decision to decide how many threads to launch, and then you call run from every one of them. And those run will block until there is any outstanding asynchronous activity. There are a few other calls, like stop, which makes all of those runs to exit. For example, you want to go away, and they will finish doing whatever they're currently doing, and then they will exit without dequeuing the rest of the work, which is in the IO context. And there is a poll method, which you can use in your event loop. It does not block if there is no work currently available to execute in your queue. And it's not a global. You can have many IO contexts. For example, if you have a multi-socket machine, you can have IO context for one CPU, IO context for another CPU, and you have affinitized threads, which essentially segregate your work between those two CPUs, so there is no sharing. And this is how an example of a code written to networking TS looks like. So we have an IO context and two timers. One will fire in 50 hours, well, 15, sorry, and another in 1 second. And in a fast timer, we will stop the IO context. So how long this program will run? Yes, 1 second. Wonderful, thank you. Excellent. So this is an example of a beautiful TCP server. And I am not being facetious. It's beautiful because it is written as a state machine, and state machines are beautiful. Pyramid of doom, callback doom. That is not beautiful. This is good. But we're going to make this code even more beautiful, live. Now, that's with networking TS. Let's look at the coroutines. So what do we have? Hey, we get 3 keywords. That's wonderful. Networking TS did not give us a single keyword. Good. Now, let's see on the library side, what are we getting? Suspend never. That's kind of not very useful, right? It's an awaitable type, so you can co-await on it. But if you co-await on it, it does nothing. It just does nothing exactly. So what else? Oh, suspend always. Another very useful type. If you co-await on it, your coroutine just suspends. So hopefully you have a coroutine handle that you can later resume the coroutine. But if you don't, you are stuck. And then it has this trait thing. I don't know. We'll figure out what it is. And that is all you get. That's why it's called naked coroutines. You open the box and there is nothing. They're useless. So together here, we'll try to see, can we take those useless coroutines and make that wonderful, beautiful networking TCP server even more beautiful than it is? Okay. So what does the next slide says? Oh, yes, but it's just, we're not going to read the specs, show the explanations of how it works. No, we will just jump to experimentation with coroutines and see what will happen. Okay. This is our hello world. Let's see Can we use the first keyword that we see there? Coroutine. Okay, compile. Nope. We cannot use coroutine in main. No problem. Huh. Easy, easy. We'll call it F, right? And then we will call it from main. Oh, it complains about something. Well, maybe it wants future. Let's see. Let's add include future, and let's make it a future of int. Maybe that'll work. Huh. Still the same problem. It says that compiler is looking for some coroutine trait specialized for the stood future of int, and also it wants in that coroutine traits a member promise type. Well, let's give it to it. Now, you're not supposed to actually specialize standard traits with types which are only built-ins or from standard, but for right now, it's an experimental TS. We can do it. Now, why compiler needs that thing? So whenever compiler discovers a coroutine, it is helpless because coroutine TS does not give any semantics to coroutine. It wants you, the library designer, to tell it how coroutine behaves. And to do that, it specializes the template, coroutine traits, with the return type and type of every parameter that was done in that function. So in this case, let's teach compiler how to deal with the future. So we'll take type name R and a whole bunch of args. In this case, we don't take any, but let's just do the complete implementation. And we'll say struct stood experimental coroutine traits. And the return type is the first one, so I will say it will take future of R and whatever arguments that were passed to the function. Thank you. That's wonderful. Look, when I was practicing, it was compiler who constantly had to correct me. Now with the audience, it's so much easier. Thank you. Thank you. OK, promise type. And yeah, that should work. Make. OK, now it wants initial suspend. So let's talk a little bit about the coroutine promise. So the promise type here is a thing that compiler will put on your behalf as a local variable in the coroutine we've just written. And you, as a library developer, can put whatever you want there. And then compiler will call you to ask some questions. So in this case, it wants to know, do we want to have an initial suspend? And coroutine allows you to suspend on the first curly before even entering the body of a coroutine. And for this particular case, we'll just say, no, just go straight in. No need to do absolutely anything. So we will use that useful suspend always and never. Never. Initial suspend. Good. So why would you not want to immediately jump into the coroutine? For example, in a generator case. In that case, maybe it takes 15 hours to get to the first value. So until somebody will actually start pulling the value from the generator, you don't want to enter the body. Or you want to have some kind of actor, which always have to run on a particular thread associated with your actor. Thus, you suspend in your initial point, and then repost the coroutine into some queue, and it will resume it to run on the right thread. And I will save you from another compilation, because I know that also compiler wants a final suspend, which is the same thing, but only at the last curly. So at the last curly, compiler gives you an opportunity to say, do you want to suspend, or you want to do something else? So if you have ref counted, for example, handle to a coroutine, maybe you want to dereference a ref count, and if it hits 0, you will just let the coroutine destroy itself. But if it's above 0, it means somebody else carries the handle to a coroutine, and you just suspend there and hope that it will be destroyed from the outside. OK, hopefully this is enough. Now it complains about coreturn. It does not know what to do with coreturn. Well, let's teach it. And it says it wants the return value. So in this case, we returned a future, right? So we need somehow to, in our return value, and to speed up typing, I just say int, because I know that I'm returning int, but properly you put template, blah, 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 blah. And here, I kind of would like to say something like this, right? I want to have a promise associated with the future returned, and I want to propagate that value into that promise. Where would we put that promise? Hint, promise type. That's why it's called promise type, because that's where we stick it. Promise of RP. Good. Compile and see what happens. Okay, now it wants get return object. It never ends. So why it wants it? Well, coroutine can return to you way before it reaches the end, maybe even at the first curly. But coroutine in C++ doesn't change the signature of a function or any way or calling convention. So when somebody calls you and it returns a future, even when the function suspends, it needs to return a future. So essentially, compiler asks, it is helpless. He says, hey, I need to suspend. Give me what I have to return to the caller because he expects the future. Easy, easy. Get return object. And where do we get the future? Yay! Yes, from the promise. Excellent. Now we're done. Ha! Now it says unhandled exception. Well, exception cannot leak from the coroutine. So there is a mandatory member of the promise which should tell us what to do with an exception if it occurred in the body of the coroutine. So we will just say p.setException, exception stood. Yeah, that's the one. And let's just to finish it off, let's say %d f.get. Go. This is our first coroutine. So we took naked coroutines and make them work with stood future. And of course, before the standard ships, we will have the proper hook into the future. But I just wanted to show how easy and quickly it is. Moreover, if you're on the Visual C++, we already throw this thing in for free because we're not very compliant with the TS. We do more, and sometimes less. And this is almost as good as it will be in the standard. The only tweaks I would make here is that I would play with the allocator of stood promise so that the shared state, which is allocated for the future, can be embedded into the coroutine itself. Thus, a future return from the coroutine is way better than a normal future. Okay, we are ready to proceed to the most difficult task. Namely, we will, go. You see, I'm using PowerPoint on Linux. That's crazy. F5, I guess? No, start slideshow. Now, start slideshow. Good. Excellent. And the clicker. Go, 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 go. We talked about that, talked about that, talked about that. Yes. So let me ask you, there is a hard way to do it and an easy way to do it. Which should we start first? Hard, easy. I hear easy. Well, my slides are done for the easy way first, so let's start with the easy way. So if you look inside of any asynchronous API in the networking TS, you will notice that initial function does absolutely nothing because the callback that you see that has to be passed as the last parameter doesn't have to be a callback. It's actually a completion token that is sent through a bunch of transformation traits, which will tell a whole bunch of things to this ramp initial function. It'll tell you what it should return, what should be passed as the callback to real implementation down below, and additionally what executor to execute it on, and what allocator to use for this function object plus whatever else is needed to perform the operation, like overlapped on Windows or some descriptor that you register with epoll on Linux. Network NTS provides a very useful thing called use_future. That tag type, if you pass it as the last parameter, it will make your API return in future. But unfortunately, we don't have a .then. So currently, we cannot really do async stuff with StudFuture as it stands today. So temporarily, just for a few minutes, I'm going to use BoostFuture because it's available and it has .then. And to do that, I will need to define specialization for UseFuture. And you don't have to understand every line here. I'm just showing you how big this thing is. It's not very big. What it is doing, it is sticking a promise, boost promise, inside of the completion handler. It's a callback that you pass to the actual implementation, and you return back a future connected to that promise. Luckily for us, future has .then, boost future, so I can await on it. So let's see what is next. Oh, again, live. Okay, get ready for me making tons of mistakes, and please correct me. So what we're going to do is we are going to take an easy way. And right now, easy is, this is a server from this performance benchmarking thing from Boost SIO, slightly modified. And let me just show you how it looks. So well, let's go actually to the server. So server starts listening on a socket, and it accepts connection. Whenever connection is accepted, it starts a session that will start reading and writing from that TCP channel. And it starts accepting again. So it's like in a loop, it reads, it accepts connection. And the session looks very similar. You start, you set some options, you start reading here, you go then write, then you read, and then you write. So you keep read, write until the connection is closed. And at any error, it'll destroy the session. So we are going to make this thing a coroutine. But before that, before we do that, let's make sure it compiles. Well, it compiles because it already compiled before. Let's start easy. So it started the server, not a coroutine yet. And I'll start the client. And we get 1, 2, 3, okay, about 75 megabytes per second. Good. Let's see how much better or worse it will become after we make it a coroutine. So server doesn't really care about the result. So how about we'll just say that our coroutine will be StudFuture of void. And that little example that we did in the beginning, how we taught compiler to deal with futures, I already put it in one of those headers. So we don't have to do it again. So StudFuture session, we'll take all args as they are, all arguments. In the beginning, we will, well, we don't need to deal with error codes because now coroutine actually can propagate the errors automatically via exceptions to the future. So we can use the version of set option that doesn't take the error. So a lot of the APIs in Network NTS, they have two flavors. One with an error in the end, it is not throw-in version, it'll put an error in the error. And a throw-in one where the error will be like this one. Okay, then we will start reading. Okay, let's just say socket, async read, and we'll replace this whole lambda with use, boost, future. Okay, we don't need this. Now, in the read, what we are doing, we are, okay, I need to say n, actually use socket s now. And I am saying async write from the socket buffer, now it's called n, and use boost future. We don't need destruction, and then after we write, we read. So we just need to say for and I think this is it. Well, not yet. We need to have a few. Let's see what are the variables here. We need to grab this buffer. Does it look good to you? Okay, let's see. Yes, 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 of course, thank you. Because that was done in the constructor. So I need to say block size. What else? Our block size here should be without underscore. And now, that's the trouble with live. So I will just divine what it is just by looking at it. Block size, buffer. You know what? I have the whole thing here already done. You know, I can just take it from here. So, yes, yes. And actually, we have this wonderful attribute called no discard. And if that no discard was on the boost future, then we would have. And I know that it'll complain that. Unused result of async write, but we don't really care how many bytes we have written. Okay, now, go. Oh, right. Of course, we converted our state machine to a coroutine. Now we need to update the call side. But it's pretty straightforward. Here, instead of creating a new session, we will just launch the coroutine, and it'll start all by itself. And I think we're done. Okay, that's good. That's good. Let's launch it. Easy. 1, 2. Ooh. I don't like that. It's like 45% worse. Moreover, here we're doing a loopback. If you do something simpler, like posting results into an executor and using a future as an intermediary, it will not be good. It will be like 10 times worse or more. So let me show you the hard way. And the good part about the hard way not only has no overhead, but it also applicable, you can use it with any library you have. Any library that uses callbacks, any C library, libuv, OS, whatever. Well, so the hard way, let's start with the result of the easy one. Any questions before I go on? No, okay, easy. Yes? Do I, okay, yes, I can. No, so. Yes, sir. Yes. The question was why it is slower. And you just triggered me. You launched me into a whole discussion why future is an inefficient type. So future has a bunch of inherent overhead. It has this shared state that has to be heap allocated. It has to be ref counted because there are two ends that operate with it. It has to have signaling when it completes and a mutex to protect the state because sometimes your .then can happen concurrently with set value. Moreover, it has to interact with the scheduler because sometimes you cannot, when you call set value and you have .then, you don't want to execute the callback in .then in the thread of set value, otherwise you blow up the stack. So what we have here, we have co-await, we just want to suspend, right? And we have an API, a network NTS, which knows how to accept callbacks, and we are creating this big intermediary to deal with that. We don't need that. And that's what we're going to do. We're going to do raw awaitables. It's more work, but it is rewarding. So let's go hard. Okay, so hard starts from the position of the easy. So it's the same function that we had before. So in a hard way, we have to return awaitables, the things that co-await natively once. And awaitable is an easy thing. It's just a struct with three functions, three members: await ready, await suspend, and await resume. Await ready will tell you whether the thing you are waiting is already available. Await resume will unpack the result. So result of co-await is whatever await resume returns. And finally, await suspend gives an opportunity for us to subscribe for notification that will tell us that whatever we are waiting for is already available. So let's start with async read sum. So we'll make a function that will be called await read sum that will take any socket, that will take a buffer sequence, return something, async read sum, socket by reference, and buffer sequence by constant % reference. Even though we're reading into the buffers, buffer sequence is just a description of the buffer to read. That's why it is passed by constant %, not by reference. And here we create an awaitable that we then return from this function. And we would like that awaitable to do all the work for us. Thus, we need to capture all of the arguments that were passed into the function and stick it inside of the awaitable. So we'll just grab this guy, and this guy will put them here. Okay. Now, await ready in this case, it will be never ready because we actually will not launch an operation until somebody co-await on us, because that allows us to eliminate a whole bunch of synchronization. So that is future is doing. So we'll say await ready, return false. Compiler sees that and says, okay, I need to suspend. So it prepares everything for suspension. And when it calls this function, coroutine is ready to be resumed. So even though technically coroutine is still running, it is calling your await resume, the standard, very graciously for us, declared that at that point coroutine is considered suspended. Thus, it is safe to call any API that potentially can call us back on this or other thread and resume or destroy the coroutine. It's fine, it's legal. So this is the place where we're going to start the asynchronous operation. So I will just say s, await, sorry, not an await, async read sum. Here we go, async read sum. I pass buffer sequence, and I pass a callback that will resume the coroutine. So I will grab this, I will grab h, and the callback will give me an error code and how many bytes were transferred. And actually, I would like to store that so that I can later access them from the resume. So I will just say here, std error code ec, and size tn. So this is how many bytes were transferred. And smart people or very detailed areas which would actually overload those two things on top of each other, because socket and buffer are only needed initially, right? And the error code and n are only needed at the end. But for simplicity, we just put all of them here. So in the lambda, we will say, well, this ec equal ec, and this n equal n, and h resume. It almost works. Unfortunately, recently we changed the specification and we said that resume is not const. So I have to put mutable here. I hope we can return that back how it was, so I don't have to type mutable at every lambda which resumes. And this is almost it. So now what we did is that we said when somebody co-awaits, it simply calls into async read sum, compiler gives them the handle to a coroutine, and whenever the thing completes, we remember the result and we resume the coroutine. The only thing left is to unpack the result. We want co-await in this case to return size t, namely n, whatever number of bytes transferred. So I will say async ready, no, resume. what happens on resume. I will return n. And to be nice, I will handle error. Is this what you said, Richard? Thank you. So Richard has unbelievable, eye for errors. It was await resume, not yes. So we saved the whole compilation cycle. Okay, if EC throw stud system error EC and yeah. So this is our awaitable, zero overhead awaitable for async read sum. Let me first verify that it compiles, and then I will do the second one. And I will remove use boost future. So now actually I'm calling an API which looks very similar to original async read, but it's the one we just created. Compiles. Yeah, it compiles. Good. Let me just clone and make another one for the async write. Async write. The rest stays the same. Async write. Do I need to change anything else? I don't think so. And I think it gives an opportunity for people who like template metaprogramming to make all of those things generated automatically from some kind of template or policy or whatever. So good. Async write here. Async write here. I remove boost future. And let's compile. Good. Let's run. Oh, there is already a server somewhere. Yes. Now we want a hard server, and let's start the client. 1, 2, 3. Wait a second. Not supposed to. Supposed to be 75. What did we do wrong? Okay, I don't know what I did wrong, so I'll just copy the good one that I know, that is here. I'll try. So we already return false. Async read sum. Looks so right. Okay, well, you know what? I'll do it twice. Maybe the second time it will work. 1, 2, 3, 4, 75. No. Let's try hard 2, just in case. Okay, hard 2. 1, 2, 3, 4. You know, I think it's like it's a browser. It's something consuming cycles. It was 75 just a second ago, and it should be 75. Huh? What if it's faster? You know, I'll kill the browser. One, two, three. Okay, good. Even the old one works slow. Thank you. Actually, we beat the old one, right? We got 60. Okay, let's get back to the slides. I have no idea how to resume it from this very slide, so we'll just click away. So what we did, it's faster with the, okay, the easy way. Okay, so what we did, we took this beautiful TCP server and we converted it into this. So I just skip a step and I also converted for you the session. So look, it actually took us about 15 minutes. If you discount the first attempt where I used boost future, we created a wrapper for stud future, and then we created the hard way the adapters that will do zero overhead communication with network NTS. And there is a hope that before we standardize, we'll figure out a way how completion token traits can be modified so that you will get similar efficiency things for free. Moreover, you will get them for free for any library which use these transformation traits plus coroutines. I already explained this. And somebody could say, well, maybe completion traits like they are today are not really bad. Maybe it's just the future which is bad. And indeed, if you play with coroutines and you use some very fancy coroutine that will get inlined into the caller, heap allocation elided, we can get rid of 2 out of 4 of these inefficiencies. We will still have to synchronize between the start an operation and a subscription. Because if you saw the example, it starts the operation first, and then you subscribe for continuation, no matter what you do. Whereas with our awaiters, we first prepare everything for the operation and only then subscribe for continuation. There are complications. But they're tolerable. So complication number 1, let me show you this wonderful... Oh, by the way, before I go into complications, any quick questions on the way? No, excellent, excellent. So this is a noisy clock. When we start this coroutine, it will start printing for us tick, tock. Well, you don't have to believe me, because we just see that sometimes tick, tock, excellent, it runs. Now let's see if we can cancel it. And to cancel it, we will start, like in the example at the very beginning, we will start the fast timer that will trigger in 1 second. And fast timer will go and async wait. That will go and cancel the timer. The one that is driving the noisy clock. Let's compile and see how it goes. Yeah. Tick. Excellent. So what happened is that we printed a tick here, then the timer was canceled, and probably at the second coil wait, async, when it was unpacking the result, discover that timer has completed with an error code, and through an exception, we caught it, we printed, we caught, so everything is great. But in this case, as a timer, I individually canceled a particular timer. But what if you want to cancel everything that is associated with the I/O context? Well, for that, you can do things like I/O stop, for example. Now I'm stopping everything. Let's compile and see what's going on. Tick, done, context destroyed. What happened? Nobody threw any exception. So, and this is not coroutine specific. This is a feature of network NTS which may get improved or not by the time it is standardized, is that when you stop an I/O context and then the I/O context goes away, none of the state machines that were driven by those asynchronous operations will get any notification. So essentially, a coroutine gets stuck. And if your process is going away anyway, who cares? Maybe that's one of the rationale. But if you have several contexts and you destroy them, recreate them while the program runs, it is not very nice. But we can solve it. And we can solve it by... I have time. By looking at this awaiter that we just built. Well, no, we didn't build, but we built the one for the async I/O, and this is the one for the noisy clock. Let's call it better async wait, and we'll call them better async wait. So we would like to get notification when I/O context goes away, so that coroutine can actually complete. So to do that, we need to go old-fashioned style. Namely, do not use lambdas. So what happens here is that this is the function object that we pass to network NTS. And when the I/O context is going away, network NTS will not resume it, but it will destroy the function object. So if we, instead of this function object, and I will just copy it because it's a lot to type, I will make it into a callback, handcrafted function object we used to do before lambdas. And then I will put it here, replace lambda with that particular object, callback. We'll pass this and Cora. Okay, let's just see what is going on here. We captured me and Cora just like before, like lambda was capturing. In the operator call, I will null out the member variable and then resume after I nulled out. And in the destructor, I will check whether somebody resumed us, and if not, I will set an error to operation aborted and resume the coroutine. Let's double check that it actually works. 1, excellent, we caught operation canceled. Now, it is not an ideal solution because it happens during destruction, and it's all done by a single thread. So if you're scalable and you want to cancel a lot of resources, you don't want to do that on a single thread. But for right now, until it's fixed, you can use this technique to deal with the state machines that just abandoned. Second complication is that we didn't deal with allocators. And we didn't deal with them, and performance was just fine because the default recycling allocator, which is used by the network NTS, is wonderful. So when your handler completes, before it is dispatched, it is copied to a local variable, and then it is freed and put into recycling block in the thread local. So that if you launch exactly one async operation from your completion, it will immediately consume that memory. So essentially, for our entire TCP server, it would only use as many blocks of memory as there were threads. However, if you launch more than one, then suddenly memory allocations would start. So you would want to change your default allocator. And it's easy to do. And we're almost ready to do because now we have this callback and we can simply add get allocator. It's one of those things that the network NTS understands. And also, another wonderful property of coroutines is that a waiter is not going away anywhere until the operation completes. Therefore, we can just say std array of the appropriate size and then tells the allocator here to use that array. Done. So those are two complications with those handcrafted awaitables. Okay, beyond the TS. So we have two possible additions to coroutines I want to share with you. So last year, I showed zero overhead future, which had none of those things. But it relied on the property that Clang had that at O2 optimization level, and if await suspend, the last instruction is resume of another coroutine, it becomes a tail call. But it is not guaranteed in any way. So Richard, sitting right here, came up with the brilliant idea. To guarantee the tail call, what if we add symmetric control transfer? So what if we'll have a flavor of await suspend which returns a coroutine handle? And it results in suspension of this coroutine and immediate resumption of another coroutine in one go. So with this particular thing, we can have zero overhead future reliably in the standard. So it's only available in the Clang trunk, not yet in MSVC or Clang 5, not part of the TS yet. Oh, another one. So another addition we might get is that people are creative. We saw that get return object in Corrosion Promise allows us to return, a future, a generator, whatever we want from the coroutine. But some people have those crazy calling conventions where function must return an error. And whatever you meant to return have to be the last parameter out star, whatever. So, and people figure out a way to do it with coroutines. Or people want to do things like they want to pass an executor so that in initial suspend, you suspend the coroutine and then resume it on that executor. And there are more flavors of things people want to do. So essentially, people want to be able to look at coroutine arguments from the promise. And the current workaround they are doing are they're overloading operator new, which is given all of the arguments of a coroutine so that it can sniff out the allocator if it wants to use the allocator. So what they would do, they will find the thing they want, stick it into the thread local, and then in the promise constructor, they will extract it from the thread local. Well, it's wonderful, but, well, no, it's not wonderful. Thread locals are slow. But we have amazing compilers that optimize their heap, they remove heap allocations. So nobody will call your operator new if a compiler doesn't need it. So we need a solution to that. And solution is easy. Actually, it was part of the original design, but we stripped it so that as not to scare people. I mean, those who looked at the customization machinery of coroutines, initial reaction is very, very frightening. So this is possibly what we can do to enable those scenarios. And at conclusion, networking and coroutine TS working wonderfully together. It takes about 30 seconds to bootstrap. Right? No, sorry, 30 minutes. 30 minutes to bootstrap. At the moment, for the best performance, you have to do it the hard way. Hopefully, we will take care of it before it gets into the standard. Coroutines are available in MSVC with /await flag and Clang by 5.0 with those flags over there. Thank you, Eric, for doing the library. Where is Eric? Eric, wave. Yes, thank you. Because it's only available with stdlib C++. And networking TS implementation, I'm not going to read it, okay? It's on the slide. One of the things I want to mention that it was already mentioned during this week that there is this wonderful coroutine library, CppCon by Louis Baker, so you can look at it and play around with it. And I promised I'm going to put the snippets I used here at that location. It's not there yet. Any questions? Well, before you ask the question, I'll show you one little thing which I skipped to speed up, but I apologize. No, but no since I see we still have time, so I wanted to compare an overhead of the future, used boost future like facility versus a raw awaitable, right? So this is a very simple thing. I keep reposting the same coroutine to an executor in a loop. And here I'm doing it with the handcrafted awaiter, very simple one. And here I'm doing it with used, sorry, not this one, where is over one, here you go. Here I'm doing it with use boost future. And in no way I'm saying boost future is not good. It's the future is not good, not the boost future. So let's start. Let's time the one with a use boost future. Okay, it's about 1 second, right? Let's time the one with awaitable. Oh, it's 0.77, so it is 10 times better or more. Okay, now I'm done.
Hello. I was wondering about the future of the TSEs, the future TSEs. Is there any work or consideration for serializing the state of a coroutine?
Okay.
It might be hard, but...
So far, we cannot come up with an algorithm that can sanely copy the state of the coroutine. I think if you can play around, the best you can do, as long as you can deserialize it at exactly the same address, it might work. But if you try to relocate it to a different memory address, imagine you have local variables, right? Some of them put in registers. And compilers, don't sometimes use indexes to navigate an array. They actually use pointers straight to the middle of the array. And when coroutine suspend, you may have a pointer in the middle of the array in some register. Now, let's serialize that coroutine and deserialize it elsewhere. How do you know how to adjust that register? I mean, maybe compiler can be super smart, but if compiler is that smart, we would not need copy constructors. It can just synthesize them for us because it's the same problem. You have some complicated class with some invariance, with some dependency between the member variables. Now, force the compiler to write a correct copy constructor.
So it's the same problem than if I wanted to serialize the state of function call, basically.
Well, it's easy to serialize the actual function call. For example, people who are doing actors with coroutines, they're suspending at initial point, and coroutine nicely captures the arguments to a coroutine and later can execute them at a different thread. So problem of capturing arguments is much simpler.
Okay.
As long as there is no relationship between the arguments.
Yeah, okay. Thank you.
Hi, Gor.
Good, Mike.
Could you, I'm sorry, I didn't quite follow what you were doing for error handling, and if we need to use error codes as opposed to, I think in most of your examples, you were throwing exceptions.
Yes,
when they're
easy. I mean, we're doing it live. Let's do it live. Yes.
I'll take my answer off the air.
Yes, so let's just go to our hard way. And how about we will, instead of throwing a system error here, if there is an error, how about I'll return -1? Right? So you don't have to throw. If you want, or actually, if we had like stood expected, I could simply return this one, and then at the call side, you will get either an error or a value. And you can do it, in many different ways. Maybe there is an extra argument to this function, and then it turns into the one that gives you either an error or a value. So it's all in the awaitables you are writing. Up to you. Did I answer your question, Mike? Okay, good.
In the easy way, there was a function which returns suspend always or suspend never. Why it's a function and not type def?
Sorry, easy way.
Yeah.
Look, in an easy way, I didn't do any awaitables. I just put use boost future, and it just worked.
Yeah, I mean, in specialization of promise type for future.
Oh, okay. In our very first coroutine we have written. Is it this one?
Yes, line 11, 12.
Line 12, okay.
So it's this function only defines what type it returns, suspend never. Can this function do anything more useful, or?
Oh, absolutely, absolutely. So, for example, imagine that we have some external handle pointing at our coroutine, right? And that external handle, and here we have the ref count. So we'll have like atomic int count. Now, in a final suspend, I will go and decrement the ref count. And if it hits 0, then I don't want to suspend. And actually, let's say bool done equal minus count. And then I will return as an awaitable struct, which will say suspend if that will take a boolean. And it's await ready, it will return that boolean. Then I will just have the same, I'll skip the rest. And here I will just say suspend if not done, something like that.
Thanks.
Yes.
Okay. From my understanding, the once the compiler encounters one of the three keywords in a function body, it assumes that this is a coroutine, and after that, it essentially makes some source level transformation of the function body into something which saves state and then restores it from some temporary storage, like have several entry points. Can you please give more insight on what exactly is done? Like when you do Lambda, there is an anonymous struct which holds all the free variables, and
okay, so I would like to refer you to two presentations, which one is coroutines under the covers, and another you can look at LLVM dev, LLVM coroutines, which go into details. But at a very high level, it transforms the function into a struct. Mm-hmm. Your initial call to a function, it's a constructor of that struct plus allocation memory for that struct.
So basically there is some call operator and there is a giant switch which enumerates something?
Conceptually, yes. Okay. But you probably saw this wonderful bragging slide.
I know.
This one, right? That all of that switch goes away.
It eliminates with compound.
Yeah, but conceptually, yes. There is a switch, there is the allocation, there is a destruction. Mm-hmm. Yeah, so it from a function creates an object with constructor, destructor, and move forward. Okay. And move forward, and the destructor have a switch because the state needs to be destroyed differently depending on which suspend point you are.
And this switch is literally a switch on some enum, or the state is more complex? Like...
It's literally initially a switch, then it compiled out.
Okay, thank you.
Sure. I think we're officially ending, but I think we can keep going.
Is there a reason there's no co-throw? I was writing some unit tests validating that exceptions worked in my case, and I wanted to write a function that always threw that was a coroutine.
What would be the behavior differently with throw than the co-throw?
The case that comes to mind is a function that coroutine that returns void, like nominally runs off the end, but in some cases throws an exception. You have co-return, you have co-yield, or co-await. A function that contains those keywords is a coroutine.
Yep.
But you can't make a function a coroutine if what you want to do is throw.
Oh, I see. Okay, I got the question. So if the only thing that is in your body of the function is a throw, you cannot make it a coroutine.
Right. You need.
Can you stick a co-return somewhere?
Well, I faked it, yes, but
yeah, because I really hated co-return initially when it was introduced, but I found a use for it. It's to make anything a coroutine quickly. I put co-return and it becomes a coroutine. So maybe that will work. But no.
Yeah, I was able to find a workaround. I just wondered if it was an oversight or what it was.
No. What if there is nothing in the body? How to make it a coroutine? So we have limitations, but it was a design choice. Other languages, they change the function signature. They put some attributes on the function itself, and thus they don't have to have those special keywords. For us, we chose not to play, with the function signature. It's just presence of those three things.
Right.
Is it possible, once you have a co-await and a coroutine, you're kind of suspending execution usually. Is it possible to start execution from there more than once? So in other words, take your current stack and make a copy of it and then resume it multiple times?
As long as you make a copy, it must be at the same address.
It must be at the same address?
It must be at exactly the same address as the original.
Okay.
Just because we don't know how to copy coroutines gracefully.
Okay.
Look at that, we are really done. Thank you so much.